Hey everyone, welcome back to another video from 197 Concepts. So in this video, I'm going to tell you how we are going to interface a stepper motor with the processor, microprocessor 8086. So I believe you all will be familiar with the stepper motor. It's just a regular motor, DC motor that rotates in a stepwise manner rather than a continuous motion. So now this steps I am assuming to be 90 degrees. Of course, you can change that. And by controlling the supply voltage that you give to the motor, you can make it rotate in a specific angle. Now, by default, it is set for the 90 degrees, and based on that angle, we are going to do the experiment here. If you wish, you can change this voltage by doing some specific changes in your code, or else the step angle of the stepper motor. Okay, so by default, it is going to be set at 90 degrees, and based on that, I'm going to show you program how to control the stepper motor using the assembly language. Of course, we can also control the stepper motor using 8051. That is another topic. Uh, Today, we are going to control the stepper motor with the help of the microprocessor 8086. Now, for simulation purpose, we are going to use Proteus, and for writing of the code and debugging of the code, everything, we are going to use the DOSBox, which is just an emulator for the Mason software. You might get a doubt that MASM is not able to develop the hex files or hexadecimal files, as this hexadecimal file is very compulsory for running the simulations, because every electronic, even the processor or the controller, microprocessor or the microcontroller, is able to run a code which is only recognizable by it, and the only language that it can understand is the hexadecimal language, a language apart from the binary language. Okay, so again, you might be getting a doubt here that all the electronic devices can understand the binary language. I'm not saying that there is no binary language. I'm just saying that this binary language, when you want to understand, when we humans want to understand, what we are going to do is we are going to convert this binary language into the hexadecimal language first. Then we are going to do other conversions. Okay. So actually, if you say in a correct manner, what you type is the high level language, and what the system understands, the microprocessor or the microcontroller, what it understands is the binary language. In between these two, there is a language that is hexadecimal language, which acts as a mediator, because you cannot directly convert the high level language that you write into binary language directly. This There is a gap understanding between the high level language and the low level language, and that gap is filled with this hexadecimal language. It's a numbering system, but we can tell this as a hexadecimal language just for the namesake. And this hexadecimal file is very compulsory for running the simulation in Proteus, and that's the main reason why we shift to the other softwares instead of DOSBox for programming the stepper motor in 8086. Okay, but today I'm going to show you how you can use the DOSBox, or how you can use the Mazen software if you are having Windows 7, in order to control the stepper motor via 8086. Okay, so the very first thing that you have to understand that there are some very strict limitations. There are very strict rules and regulations in order to convert the hexadecimal file, in order to create the hexadecimal file from the high level language or the assembly level language. To be more clear, I will speak in terms of assembly language. Okay, so first of all, you need a hexadecimal file for running the simulation in the virtual, even the virtual simulation, or if you have a kit, you can directly dump it. But that too, it has to be a hexadecimal file. Okay. So as we are doing here the virtual simulation, I will stick to that. And in order to run that simulation virtually, you have to create a hexadecimal file, which by default is not able to be converted using DOSBox. Okay, so that means by using Mazen, you're not able to create a hexadecimal file. That's why regularly or generally people shift towards the other software instead of DOSBox. just now I've told you, we can convert the regular assembly language file into a hexadecimal file, but using DOSBox, but there are very strict limitations. So the very first limitation, for just for your knowledge, is that you should not be creating a separate module in the assembly program that you are going to write. For example, or I can say that there should be a no new stack creation. Okay, so by default, when you are running the program or when you are executing the assembly level language, you definitely are going to initialize the stack, and it should be initialized only once if you want to convert that particular program into hexadecimal code. Now, if there is no such need for converting the your assembly language into the hexadecimal file, you can make the modules, no problem. But since we are using here, or we are converting the program file or the assembly language program into hexadecimal file, definitely for one limitation is that I should not initialize the stack segment twice in the same program. Okay, that's a very big limitation, and there is a size limitation of the program file that must be some limited size. Okay, if that's size or amount of the size is going to increase, definitely the conversion is not able to happen. Moreover, uh, there are two types of files, or we can say that there are two types of hexadecimal files that we will be talking here. Okay, just a second. So when you are going to convert the ASM file into hexadecimal file, okay, there are two ways to tell this. Okay, this file, this is bin file and hex file. Okay, so I have tried with the hex file, but I don't know, I did not get the output properly. Maybe a conversion problem, but I get the output properly with the bin file using proteas for simulating the circuit. That's why we are going to move with the bin file instead of going with the hex file. This is for some other topic. I will do it, I will try to make it work. Okay, for this we are going to use the command exe to bin. Okay, this is the command. Of course, there's some other thing that you have to type. I will tell that in the program. uh, and for hexadecimal file, in order to convert the your assembly language into the hexadecimal file, you're going to use the command bin to hex. So this is the procedure. So if you want a more clear idea, so after typing the whole program, first of all you're going to do masm your file name dot asm semicolon. That's the very first command that you're going to execute. If you're not having any errors, then you go for link file name dot obj. That's the second command that you're going to do. And the default third command is af debug file name dot exe. This command we are not going to follow just in the case of stepper motor, because we need hexadecimal file. Instead of this, we are going to use the command exe executable file to bin file. Okay, bin file, uh, file name in its exe form space file name in its bin form bin. So since it is a case insensitive language, you can either use the what we say capital letters, or you cannot use, you should not you can use the capital letters, also you can use the small letters also, or you can use combine both of these two. So that's not a problem, since it is a case insensitive language. So instead of just using AF debug, this will take you into the green screen where you execute the program and rectify the logic cycles or the logical errors that you will be able to find only after running the program. But this command exe2 bin will convert the executable file, executable file that is created after the link command into the binary file. Okay, so binary file. Since it is this command is converting your executable file into the binary file, and at last the microcontroller or the microprocessor is able to understand only the bin file, that is the binary language file, that is the binary language file. So there is no need to convert this file again into hexadecimal file. Since again this hexadecimal file, when you load into the processor, when you load into the microprocessor, it will again be converted into the binary file. That's the main purpose. We are not going towards the hex file. You can use the bin file, but in some cases where you need only the hexadecimal file, after using this command, you are going to use this command bin2 hex. Okay. So once again, I'm going to write the what I'm again once again going to write you this steps that we are going to use, that we will be using. Okay, the very first one is mazen your file name dot asm. This checks the syntax errors and converts your and forms your object file. And then next we use link file name dot obj object file, and by default you are going to use af debug. Okay, for debugging your file. So there's a dot here. But instead of this file, this command, you are going to use, since we are going to convert this into a binary or hexadecimal file, simply instead of running this command, we are going to use this, what I'm going to write that command. Okay, that's exe to bin, okay, file name dot exe space file name dot bin. After this, the fourth command that you are going to use is bin to hex file name dot hex. So this is the file name of the binary file. So this will be more, you will get a more clarity when I'm going to execute it. And this is the name of the hexadecimal file that the program is going to create after executing this command. Okay, so now let us understand the program code. The very first thing, so this is the circuit, this is the program. And the very first thing you have to know is that you can rotate the stepper motor in two directions. I'm not talking about the steps, I'm talking about the directions. You can rotate the motor in two separate directions, that is the clockwise or anti-clockwise. The synonym of anti-clockwise is counterclockwise. So you can rotate the stepper motor in clockwise direction or in the anti-clockwise direction. Okay, I'm going to explain you the code that is used to rotate the stepper motor in clockwise direction, and it's the same code for rotating the stepper motor into anti-clockwise direction. Or there's a small change in the logic. I will later explain you that. Okay, so this is the program that we are going to use in order to rotate the motor in clockwise direction. So just let me take my marker. Right. The very first command that you are able to see here is uh, Okay. So the very first command that you're able to see here is dot model tiny. Okay. This tells us that whatever the program you're typing here is just of, you have to convert it into the tiny space. Okay. So when you're executing or when you're converting this program, that is your assembly language, that is by using the command masm filename dot asm. When you're using this, you are going to have a dynamic allocation of your program, the dynamic allocation of the size of the program. When you use this command dot model tiny, okay, this tells that you have to convert this into an object file, but the size has to be very minimum. That's the reason we are using this code as this command, as I have already told you, in order to convert the masm file or the assembly file into the hexadecimal file or the binary file. There are very strict regulations in the masm software. So since we are using masm here, definitely you have to use this command. Then next, this is just a indication that our program is going to start here. And org 100h, this is tells us that all your registers that you are initializing are going to start at the 100h location. Okay, not the 100th. This is the hexadecimal 100th location. When you convert this, this gives a separate meaning. That's some other information which I'm not going to share here, as you might get confused. Okay. So this is 100h is in hexadecimal. You have to convert this in decimal form. That means you have to convert that in 100D. How is that conversion possible? You already know that procedure. I will share the link of that video also, how to convert the hexadecimal, or how you are going to convert any hexadecimal values into the decimal values. Okay. So that's it. That's the main thing of the three lines, and that's the initialization of your program. Then by default, you're going to use the start label that tells you that your main code is going to start from that section. Okay, and here comes the magic. So let us erase this all. Yeah, that's a shortcut used for deleting it. Now, the very first command that you observe here is move al80h. The very first command that you're going to see here is move al comma 80h. This 80h is split into two separate digits, and it is converted into the binary form as 100000000. So this is 8421 code, this is 8421 code. That's the binary representation of 8, and this is the binary representation of 0. Why we have to convert this? This represents the 8-bit digit that is used to load in the control register of 8255. Now, 8255 is nothing but the programmable peripheral interface, and in order to use the port A register of programmable peripheral interface, you are going to use this number 80H as the control word. Since you have to set the port A of a peripheral interface, port A of 8255 or programmable peripheral interface as output, you have to use this command 80H, or you can say the number 80H. Okay. Now this 80H also in 8255, we are going to have four types of registers. So three are the port A, port B, and port C. So that's PA, PB, and PC. And the main register that controls the 8255 is the control register. This register tells what type of or in which direction the port A, port B, and port C is going to accept the data. Okay, in which direction they are going to move the data, either in the sending format or in the receiving format. Now you might ask, what is a programmable peripheral interface? It's just an device that is used to interface between the IO devices, input and output devices, and your processor, in order to reduce the uh, what we say, the working load or the working pressure, or yeah, the working load of the processor at that particular instant of time. Okay, so in order to select this control register, in order to select this control register, you are having, see, we are having four registers: PA, PB, PC, and the control register. Now, at one particular instant of time, I'm going to use only any one of these registers for sending or receiving the data from. Now, I need to send a data first initially to the control register in order to set any of the ports as uh, the input or output port, the split mode, or whatever. You have to know the working of PPI because there are three modes in a total, three modes in a total of PPI. Okay, so that's some other topic. So in order to activate these three registers out of one mode, from out of these three modes, you have to use the control register. This control register can be accessed, or any of these registers can be accessed by using two lines, namely the A1 and A0, that are present on the PPI, programmable peripheral interface. The IC number is 8255. Okay, so these two lines are used to select any one of the registers. So why we need to select those registers? For example, I'm going to send data, just in the case of our, for our example, we are going to take our program itself. I am going to connect the port A with the stepper motor in order to rotate it. Now, when I'm going to send the data, when I'm going to send the information that is used to rotate the data, that is used to rotate the motor, definitely I have to send it to in towards the port A, not to port B, not to port C, not to the control register. For that, I'm going to use A1 and A2 lines. Sorry, A0 and A1 lines. Okay, now. So since we are having two inputs, I'm going to get four different combinations. That is 00, 01, 10, and 11. For 00 combination, I'm going to select port A. For 01 combination, I'm going to select port B. For 10 combination, I'm going to select port C. And for 11, I'm going to select the control register. Okay, now initially, so this is the main scenario behind the first three lines, this 80H, 06H. Okay, now if you have got a clear idea why we are going to select these three lines and what is the need of these A0, A1 lines and these three registers, I'm going to dig into these steps. Okay, so into those commands. Okay, so let me just select the marker once again. There you go. I've selected the marker. Now, our first line is you have to move the word AL into the ATH, right? That's the very first thing. When you convert this ATH, the 8 bits that you're going to get is 1000000. This tells us that you're going to use port A as the basic IO port. That means in the mode 0, mode 0. Okay, so that's the meaning of this, that's the meaning of this first line. Now the second line, move dx comma 06h. Okay, so move dx comma 06h. When you are going to convert 06 into the binary language, for 0, for 0 the binary code is 0000, whereas for 6 it's 0110. Okay, 0110. When you see this is completely zero, this is of no use for us at this instant. When you observe this code, that is 0110, this, what this does is, what this does is, where you're getting the logic ones, that are your lines A1 and A0. Those are your lines A1 and A0. Now, since A0 and A1 both are logic 1, you are going to select the control register of 8255. Okay. Now, after doing this, you're not staying there. What you're doing is you're going to send the data ATH by using the DX port. Okay. Here the command out, OUT, sorry, not there, here, out. dx comma al. This tells that the data that is present in al has to be moved out of the 8086 by using the port dx. Or you can say that if you are having 8086 processor microprocessor, the data has to go out of the 8086 microprocessor by using the register data dx register data register dx. Okay, which value that is present in the accumulator register. So that's the main purpose of this out dx comma al. This line is present at every segment or every part where where the main step is used to rotate the stepper motor. Okay, so now the very first thing is, first of all, you're going to load accumulator register with the value 80h just to select the mode of operation of 8086, not 8086, select the mode of operation of 8255. That is your programmable peripheral interface. Whereas the second line is moving the value dx or loading the register dx with the 06h value. Okay, this particular value 06h is going to be stored in dx, but it is not necessary to move this value out of the 8086 processor, as we are going to shift the value 80h into the accumulator register and moving it out of the dx register. So this value, there is no such thing to do for this value, because by default this is going to be accepted by the control register. Here the comment itself is saying config register address. So this 0006, we are only writing this. We are just writing this command in order to select the control register of 8255. So my only purpose is to activate the lines A0 and A1 of 8255. I will show you. So I will show you the circuit later. There you can get a clarity. Okay. So it will be much better if you note this somewhere in the notes for further analysis. So that's the three lines. That's the meaning of three lines. So just moving 80h into the accumulator register, and before sending it to the 8255, we have to start we have to initialize the 8086 by using the control register. So now in order to select the control register, you are using the word 06h that is going to be stored in the data register dx, and later the 80h value is going to be loaded into the dx, and that dx value, that is the 80h value, is going to send to the 8255 via the dx register. That's the initialization. That's the initialization of the complete program. Now, after that, our program is going to start. That means from this rotate label, from here onwards, our program is going to start. Now, I have initialized the port A in mode 0. I have initialized the port A in mode 0. And for initializing this, I have set my control register also. Now I can type my program. So first of all, I have to send the data, that whatever is present into the PA, to clear it out. That's my wish. Either I can use that program, but if you are continuously using that and that particular port, and you are going to dump this program again, there is a chance that the previous values are going to stuck into the particular port. In order to clear those values, in order to clear the port A value, I'm going to use this line. So this is just moving 00h into the DX, and later on I'm going to use that in order to move it into the clearing out of the dx register. So this line, the first line, move dx comma 00h, is used to select the port A. As you can see the comment line here, it is used to select the port A, and this line is used to clear out the values that were present in the dx register. Be mindful, when you are using the out command, you should use it only with the register accumulator register. Okay, na? For example, if you're going to write, sir, you might ask me that we are first of all loading accumulator register with 00h, okay, and then This double zero H is going to be loaded into the DX. Why not if we write the output DX comma double zero H like this? So this might sometimes cause an error because when you are sending the data or receiving the data out of your microprocessor or microcontroller, definitely it has to touch the accumulator, not accumulator, it has to touch the ALU. Okay. Now this ALU is not able to directly load the data. First of all, it is going to store its data somewhere, and that somewhere is nothing but your accumulator. So there's a spelling mistake, accumulator. Okay, so ALU is going to store the data into the accumulator, and from there it's going to grab the data. For that purpose, that's the same for either you when you're sending the data or when you're receiving it. That's the main reason when you're using the command out with any register, you have to use the AL register. Okay, that's the main purpose. Whenever you are observing here, also when you're loading this value 9009 into the accumulator, you're going to move this value 09H into the 8255 in order to rotate the motor. But since that 09H is going out of the 8086 microprocessor, you have to use it with AL. So you can ask me, sir, why we are not able to use out DX comma 09H? It's the same reason that when you're sending the data out of your microprocessor, definitely it has to touch the ALU. Okay, for that you have to use out dx comma al, and al must be loaded with the value 09H. That's the main thing. And apart from that, there's nothing else in order to explain in this program. So if you have understood this logic, then I'm going to speak about the stepper motor. That's it. And I'm going to tell you why we have written these values 09, 0C, 06, and 03. Okay. Now, you might be familiar that in order to rotate a motor, you are going to have two components. The very first one is stator, and the other one is rotor. This is rotor, and this is the stator. Now, for this stator, there are going to be two. I'm going to take, let us take another color, like let's go for green. At the stator, you are going to have poles. This is the north pole. This is the south pole. In the same case, this is the south pole. This is the north pole. Okay. Now I'm going to give names as A, B, C, D. Okay. So this is the north pole, south pole, south pole. So these are the basically magnets, and in between those magnets, when you're going to energize those magnets by using power supply, your motor is going to rotate. That is nothing but your rotor. Okay, so that's the logic. And these magnets are special kind of electromagnets, and you might be familiar with electromagnets. So the magnets that are going to energize only when you give a power supply are called as electromagnets. Now my logic is that if I want to rotate my motor, so the rotor is also a magnet that is having a north pole, a south pole. So let us go with some other color like yellow color. Okay, so this is the north pole, this is the south pole. So this is not visible at all. I will select blue color. I believe this one will, or else, yeah, I will go with blue. So this is the north pole, this is the south pole. When I'm going to energize this A, okay, when I'm going to just energize this A pole, So this north pole and this north pole is going to repel each other, and in order to uh, also this B pole is going to repel the south pole of the rotor. Now I need to be very careful of the directions, because if I am going to energize this one, this will rotate the clock, rotate the rotor in anti-clockwise direction. And if I'm going to energize this north pole, this is going to rotate the rotor in the clockwise direction. So that's the logic. So for that, I'm going to write a truth table A, B, C, D. Okay, A, B, C, D. Now, first of all, I'm going to energize the two. First of all, I'm going to energize the two poles, A and B poles. So that's why I'm going to send logic ones for those two, and these two logic 0. Then I'm going to energize the C and D poles. So that's the other poles. I'm going to shut it down. A, B is going to be 0, C is going to be 1, 1. Okay. So these are the input combinations that I'm writing for the four inputs. So these are the input combinations. The another way is energizing the magnet, energizing the north pole of A and the south pole of D. So this is 1, 0, 0, 1. And finally, what is the another combination, or what is the another possibility is energizing B and C. So 0, 1, 1, 0. When you observe this is going to be 6, and this is going to be 9, this is going to be 3, and this is going to be C, because this addition is 13, and the representation of 13, sorry, it's 12, not 13. The representation of 12 in hexadecimal is character C. Okay, that's why I'm going to write 09, 0C, 03, and 06. So 09 is 0000, 1001, 0C is 0000, 1100, then 03 is 0000, 0011, and finally 6 is 0000, 0110. Okay, so that's the main reason why I've written 09, 0C, 06, and 03. Those are the four words that I'm going to use. Other than those words, I'm not going to use anything else. And in order to send these words out of the 8086 to the 8255, I'm going to use the command out. And in order to see the output or see the rotation for after the completion of every command, that is after the completion of 09 and 0C and 06 and 03, I'm using a command delay in order to give some time for them to rotate. That's it. That's the complete logic. Okay. Now this logic I have written here C396. Don't follow this command. Okay. If you follow this order, not the command, if you follow this command, this order, your rotation might not be in a proper format. The proper format is this one. For clockwise rotation, it's 09, 0C, 03, and 06. Oh, these are interchanged. So the correct order is 09, 0C, 06, and then 03. This is the correct order. So based on that, you can make the hexadecimal value representations, and you can analyze this circuit. Or else, if you take A, B, C, D in a regular format, so very first thing for 09, so I'm going to use A and D. I'm going to energize this one, and I'm going to energize this one. So this, what is this is this north pole and north pole are repelling each other, but this, so this north pole repelling this thing, so that's why it's going to rotate in this direction. Okay. You might ask what is going to happen. This, based on your configuration, either it's going to attract or it's going to repel. Basically, this is the magnet, and this is also a magnet. So that's, I'm going to energizing D. Mm, that's what is going to happen. Okay. So experiment on this order. You are going to find your order. I have tried it. I have after so much trying. So 09, 0C, 06, and 03 is the final order that for my motor it's going to set. Also, there are different types of motors in stepper motor, that is unipolar, and again there is bistepper. Not bistepper, bipolar. So based on the polarities that you are going to use, there are unipolar and bipolar, and based on that also this combination is going to change. What combination? This 03, 0C, 06, and 09 combination is going to change. So you have to just try and error this. And for stepper motor, the basic order is 09, 0C, 06, 03. Okay, so no doubt in that. That's the main thing. And if you have understood this logic, definitely you will be able to understand the simulation outputs also. So that's all. There's nothing else in the program to understand. If you observe, we are going to initialize AL with ATH in order to select the in order to select the port A of 8255 as the output port. But before that, we have to initialize, or we have to select, we have to tell the 8255 for selecting the port A as an output. And for that, you have to use the lines A0 and A1, or you have to activate those two lines A0 and A1. For that, you're going to use the uh, word 06. Then we are going to enter into the rotate command, or rotate label, where initially you're going to clear out the port A, all the values that were initially in the port A, and then you're going to load 09, 0C, 06, 03 in a stepwise manner. What's going to happen after this? Nothing else. There's just this delay procedure. Okay, this procedure is nothing but this procedure. In this procedure, what I'm going to do is, first of all, I'm going to load the CX register with the value double F double F H. Okay, now after completing one delay, or not one delay, after executing this call delay function, it's going to go here, and definitely it's going to just see here, you're going to loop L1. How many times is based on this count. So for the first thing, it's going after executing, after meeting this command loop one, what it's going to do is it's going to check CX. So it's going to check CX, and for after checking the CX, it's going to verify if it is having some value other than 0. If it is having a value that is equals to 0, it's going to come out of the loop. Since we are going to have here double F double FH, it's going to jump from L1 to again towards this value L1. But after that, your double F double F value is going to be reduced as double E double triple F E H. So this cycle continues until you get all four zeros. You might think this is a huge delay, but for simulating, or when you're using Proteus, the delay is nothing. We will see that. Okay. So the new things that I have to tell you here is the delay procedure. Okay. So delay procedure, PROC. This tells that the commands that you are going to write here are nothing but the that comes under the delay label. Okay, so this is the professional way of telling the procedure, that function, you say it as a function, and this is a informal way. That's it. There's no difference between that. And in order, if you are starting this procedure, you have to end it also with the command delay end procedure. Okay, that's what we are going to write here. And finally, we are going to end the start command. Okay, so that's the explanation of program. Now let us execute. Let us try to execute this. I'm going to remove this. I'm going to minimize this, and I'm going to start the DOS box. Okay, I think it's going to, yeah, I thought about this. And one more thing, I have to tell you about the anti-clockwise. If you observe the program, you are going to use more tiny dot code, same origination of the registers, and ATH. First, you are going to load ATH into the accumulator register. Then you are going to send 06. Then you are going to send ATH to 8255, and initializing the port A address, and clearing out all the values that are present in port A, And if you see here, what you're going to do is 03, 06, 0C, 09. Here you're going to change the order of the sequence that is used to rotate the stepper motor. So what I have told you is, if you are sending 09, 0C, 06, and 03, this order is going to be used for clockwise rotation. Clockwise rotation of the stepper motor. Since clockwise is opposite to the anti-clockwise, or we can say it in the reverse way, anti-clockwise is the opposite direction of clockwise. What you are going to do is, you are just going to reverse this cycle like 03, 06, 0C, and then 09. That's the only difference you are going to do. I'm going to show you the simulation of both the things. Just stay with me. So I have to first open the DOSBox application. So DOSBox application, and these are the basic commands. Mount C colon backslash. I'm going to clear out the screen. Now I'm going to change from from Z drive to C drive, and changing the directory to 8086. Now I need edit. Okay, I have opened here. I have to copy and paste here the program, or I have to type it, but I have already done that. So I'm just going to open it. I have stored it with the smclk.asm. Okay, so this is the same code that I have explained to you there. I have tested this. This is the working method. This is the working program. So yeah, this code, you might get a doubt here. Where is the delay end? It was hiding somewhere else. So this is the complete program. I'm going to execute this. See the name smclk. Okay. So file exit. No need to save that. Now our basic steps. Masm smclk.asm semicolon. Done. No warnings. Then I'm going to link it. Link smclk.obj. So linking no problem. Now generally we go af debug. Let us do this. smclk dot exe. So this will open you this debugging screen, and when you go for ATH, AX80H, DX is going to be loaded with 06H. Now DX is going, AL is going to be overcopied. So see here, after executing this command, the dx is not overwrite with not written with overwritten with 06. It is just as it is. There is no change in the value of dx. What we are doing here is, by using the data register dx, we are sending the value 80 into the 8255. That's the difference between move and out command in the assembly language. Okay, so I've executed this, and see, the value has changed here because I'm using the move command. And also AL, I'm going to initialize it to 00. All the values are going out of the DX port, out of the microprocessor 8086 via the DX port. And again, A9 is going to be loaded, and that A9, observe the DX register here. It's not going to change. It's just going to stay at 0000, but the value is going to be sent to the 8255 using DX register. See, I have executed it. Now call 0126 means we are going to move towards the delay value, where the CX value, which is 012C, is going to be loaded with the double F double F. Now loop 0129. 0129 is the same line where I'm staying at. If I'm going to press F1 again, observe the value of CX. It's FE, and it's going. If I'm going to press it continuously, the value is going to decrease. So this is going to happen for all the four digits. That's, see, it was triple F some value. Now it is FE F7. So this is going to be reduced. The values are going to be reduced until it's 0000. So this is the way of executing. So just escaping from that. complete value. Now I've pressed just F2, and it is assumed that the system has completed the CX limitations all up to double zero. Since double zero double zero, since CX value is all zero 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 zero, it's not going to execute the loop again. It's just going to return where it came from. So it came from 09 after the value after the line 09. Now it's going to load AL with 0C. Again, it's going to call 0126. That's again, it's going to load the CX with double F double F, and it's going to execute, and then it's going to return again to the main program. So that's it. You won't be able to see the code. You won't be see the output here properly. You need a proper circuit in order to see the proper output. For that reason, you have to convert the executable file into the binary file. Now observe this. So you have used the command afdebug. You have used the command afdebug. Now what I'm going to do is I'm going to convert this executable file into binary file using the command exe2bin space. What is the executable file? smclk dot exe. What is the name that I'm going to create is that is a binary file. What name I should give is that's my wish. I'm going to give the same name smclk dot bin. Okay, just press enter. That's it. It's going to create a binary file in the backend. No problem. You can go and check it in the 8086. Okay, in the 8086 folder. Now I'm going back to the windowed screen, and that's it. That's a part of DOSBox. Now I'm going to the circuit diagram, which I've already designed. And if you observe here, the very first thing is done the program. Okay, SMACLK. I have already that in anti-clockwise also. I will show you the output also. I'm going to load first of all the SMCLK, which is nothing but the BIN. Observe the extensions. This is the assembler language file, assembler file. This is the binary file. I'm going to select this, open it. Okay, and then click on OK. Oh, it's just SMACLK. I need SMCLK binary file. Selected, open, and click on OK. That's it. And when you see at the circuit, these are the connections. This is going to take a little bit of time. So this device that you are going to see here is okay. I don't think that you're going to need a pen here. Okay. So this device, what you are seeing here is your 8086 microprocessor. So these are all the pins. This is the address bus. The way this address bus is possible for you to find is just let me clear this out. Just go into the terminals mode. I believe it's terminal mode. So explore the objects. Yeah, it's a terminal mode. You're going to get the bus. So if you place this and if you're going to connect it in this manner, you're going to get the bus. Okay. So that's the base. That's the bus is placed, and then you can connect it as usual. Now components mode, and I will let me zoom it in it properly. That's the whole circuit. So this is your microprocessor 8086, and this is the interfacing device to interface the peripherals, or you can say programmable peripheral interface 8255. The other two devices or other two integrated circuits, this is the 74HC373. You will be able to see the number here. So this is nothing but your latch. LATCH. Why this latch is used? See, you're going to have the data and address lines from 0 to 15 multiplexed as a single lines. So in order to separate the information that you're sending here, or you can say that in order to let the 8255 know what you're sending, either the information or either the data or the address. For that differentiation, you're going to use this device. Okay. If you observe here, the OE, that is enable pin, is active low. That's why I've placed a logic probe here and I've connected in the logic 0 mode. That is same for chip select. This is the active low pin. That's why I've used the same logic state in order to activate this device. So the address is going to send from here towards this one, and it's going to differentiate whether I'm going to send the data or the address, and then it's going to use. See, I'm just using A0 and A1 lines. I just need A0 and A1 lines in order to select the control register first, then the port A. This port of 8255, I'm not going to use this particular port, and I'm not going to use this particular port. Okay. So only for that selection, the selection between port A and control register, I'm going to use two lines, A0 and A1. You might be familiar with read and write pins. You might be familiar with reset pins. And again, the D0 to D7 is multiplex address and data lines. You have to name these also, the particular lines as AD0, AD1, AD2, AD3. Otherwise, your bus is not going to work. Be mindful of that. And finally, this one, U4, that is ULN 2003A. This is nothing but the driver circuit. So this is one of the driver circuit. In Proteus, we are having two drivers. That is this one, ULN 2003A, and the, I believe, L293D. These two drivers are used to rotate the stepper motors. So what kind of stepper motor I'm going to use here is unipolar stepper motor. Okay. Don't get confused with the directions or with the connections that you're going to see here. The unipolar stepper motor is having 6 pins. In order to connect it, 4 pins are excitation of the coils, and this is the common pin. Okay. I will just zoom it at the motor. So if you observe here properly, I'm going to make it okay. All the pins are okay. I will just delete the lines. We can reconnect those. So this is the motor, and these six are the pins, and this is the common point for coil A and coil B. This is the common point for coil A and coil B, whereas this is the common point for coil C and coil D. Okay. So that's why these two, the common points are going to be connected to the power supply by default, and the other four pins are going to be connected to the driver, that is ULN 2003. That's what the connections are. So these are the connections. Now, if I'm going to zoom it properly, the whole circuit should be visible. Okay. What I'm going to do is you observe the pins here, 4, 3, 2, 1 pins, and see the rotation of the motor. So I'm going to start the simulation. Okay, the simulation started, and it's going to 9 plus 90 plus 180. This is just to see the overall circuit, and then I'm going to zoom it in this direction. What we are going to do is we are going to analyze it in a stepwise, in a frame by frame manner. Okay, so this is 0 degrees. Stop, just pause here. Now, if you observe here, we have to go from the highest to the lowest. So when you're going from highest to the lowest, what are the ports that you're going to get are, yeah, this will be much better for writing. So what are the ports that you're going to get here? The ports the pins that you're going to use here are from the port A are nothing but the P3. Oh, that's not visible at all. I will go with blue. Yeah, blue is visible. The ports, the pins that I'm using are PA3, third pin of port A. The black is much visible. I don't need this one. PA3, the next PA2, the next PA1, and the next PA0. Now observe here, the motor is at 90 degrees of rotation. The motor is at, I will write it once again. So the motor is at plus 90 degrees of rotation. Okay. And the observe the logic here. PA is at logic 0, PA is at logic 0, PA2 is at logic 1, and PA3 is at logic 1. So this thing completely gives you the combination of 0C, right or not? 8 plus 4, that's 0C. So you might say me, sir, we have missed the value 0, 9. So that is initially possible. I will go from at the starting. So I'm going to stop the simulation and I'm going to run the simulation. Observe it. So this is 0, 0, and observe the value. First of all, it's before going for C, what are the values here? If you observe there, the red dots are the logic ones and the blue dots are the logic 0. So this combination is 0, 9H. So for 0, 9H, there is no motion, but when you go for the next step, you can observe the delay here. You can observe the delay here at the bottom of the screen, just at the side of this where I'm pointing the cursor. When I'm simulating, you're going to get the 4 milliseconds in calculations. I'm going to just run this. Yeah, when you're going to rotate it for 90 degrees, observe what is the value you're going to get here. That's 1100, which is nothing but your 0CH. And then again, when you're running this, when you're at 180 degrees, what is the code that you're getting? That's 0110. This is nothing but your 06H. And finally, when it is at 270 degrees, what is the code? It's 0011. So this is nothing but your 03H. Okay. And then finally, now you will get a clear understanding that, yeah, when it is again at 0 degrees, so this 0 degrees is nothing but either 0 degrees or 360 degrees. Both are same, 0 degrees or 360 degrees. So if you observe the logics here, that's nothing but 1001. Okay, so that is this logic. So 09H represents either 0 degrees or 360 degrees. If your stepper motor is at what we say, you just need to stop the motor at 90 degrees, then you can stop the code at 0C. So this will rotate the motor for 90 degrees. Now the other thing that I told you is the steps, right? So this is the rotation of stepper motor in clockwise direction. That's it. That's a complete experiment. Now, if you double click this, you're going to get a step angle of 90 degrees. If you reduce it for 45, now just observe this. When I'm going to run it, the angles are going to be at an increment of 45, 45. So that's a complete 180. Okay. It's going to again rotate into the same manner. Now, again, if I am going to stop this and change this angle from 45 to 10 degrees, let us see what's going to happen. 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90. So as you decrease the step angle, it's going to make a smoother run. Oh yeah, now you might tell me, sir, this is a very slow simulation. For that, you can increase the RPM here. So that's at 360 degrees. I'm going to increase it for 500. But in order to do that, you have to increase the step angle also. Now see here. That's very fast and jerky movement. That's very fast and jerky movement. So I'm just stopping the simulation, and from 500 I'm going for 50 rpm. Now just observe the rotation of the motor. The steps are 90 degrees. This is a very smooth operation, right? So that's the difference. That's the settings you can do. And I have to show you the operation of stepper motor in anti-clockwise. Since it's the same program, I've already typed it and I've already created the binary file in the same manner. I'm just going to change from SMACLK to SMCLK to SMACLK. So there's my binary file for anti-clockwise, and there's my binary file for clockwise direction. I'm just going to selected, and then run this. Okay, observe here. So let me just stop the simulation again and run it. Yeah, observe the values. Yeah, we have to write the values also, right? So I'm going to place it here. Now I'm going to run it, and I'm going to first stop it. So again, I'm going to write those values as PA3, PA2, PA1, PA0. So if you observe there, if you observe here, these four pins, these two and these two, not this one. If you observe these four pins, what you're going to get is 1, 1, 0, 0, which is nothing but your 0, 3, H. Observe the angle here. It's not exactly 90 because I have not rotated it for, I have stopped simulation, paused the simulation earlier. So the RPM is slow. That's why it's a little bit slow. Okay. Okay, I will do it one more time. So I'm going to select that, and I'm going to select the RPM as 100, 90 degree step. Now observe this. Yeah, see, that's 89.8. That's roughly 90 degrees for this value. And then when I run this again, when it is at 180 degrees, observe the values here. That's 0, 1, 1, 0, which is nothing but your 0, 6H. Then run this, pause it, and note down the value, which is nothing but 0011, which is again 0CH. And finally, so observe the angle, it's minus 270 degrees. Yeah, minus 360, or it's 60 degrees. Again, that goes to the value 1001. So 09H. Okay. So that's, if you observe this, that's a complete reverse order for the clockwise direction. So that's about this program. I hope you have understood the logic behind rotating a stepper motor in clockwise and anti-clockwise direction. And if you have any doubts, you can ask me in the comments. Okay. Thank you. That's it for now. And I'm signing off. Thank you very much.